Florida's recent report on the state of the clean energy job market in New York. It's growing at about twice as fast as other ends of the sector. In tight job markets, might be a good way to look for opportunities. And Oneonta is actually at the forefront of a lot of relevant projects in these areas. And actually, I'm not going to say any of them because they're coming. We are grateful to have with us Lachlan Squair, who's VP of Facilities, and Cindy Lehr. Did I say that correctly? Yep. And Cindy, I don't actually know what your title is.
Yeah, I'm the capital program manager of the department.
And what they're going to do today is actually discuss in pretty good detail a number of super interesting decarbonization projects related to energy on campus. And if you listen to the news, energy is everywhere. Okay, it's how we get it, how we use it, what its impact is. All right. Tell me three things, three recent stories you've heard regarding energy. Yes, sir.
I think somewhere on campus is like a neutral energy state on campus.
A neutral energy state. If I understand you correctly, that's where we're going. And I think that will be addressed in some state.
I saw something on LinkedIn. I can't remember exactly.
Carbon neutral.
Yeah.
Okay.
Carbon neutral.
Yeah.
Carbon neutral. Yep. That's what I was assuming. Yep. And so getting there, and we know why that's important. Anyone else? Energy use going up or down? Up AI. So that's a concern. All right. Something else. Go ahead, Paul.
I was going to say that I heard they're messing with the offshore wind projects. Some of them are getting.
They are, but a judge halted the nesting in Rhode Island in a decision today. So 14,000 people might be going back to work. Okay. So anyhow, we'll see. You don't have to look very far. All right. I think I've done enough.
Sure.
So my name is Lachlan Squair. I'm Associate Vice President of Facilities here. My background is I did a degree in engineering a long time ago in Australia, as well as a degree in applied management. Moved here to the United States in 2000. I've been working in facilities, higher education for about a little under 30 years, and I had about 10 years in heavy industry prior to that. So my area, we look after all the construction on campus, operations and maintenance, space maintenance, space inventory, health and safety, all of our clean energy stuff, all our decarbonization, renewable energy, energy management, energy procurement, maintenance and operations, the whole, everything to do with the physical university itself.
I'm Cindy Lehr. I went to school for civil engineering, so I had a lot of physics classes, and we had TAM classes. That was theoretical and applied mechanics, and I'm also a professional engineer. And for the first 3 years of my career, I worked for a design consultants, and then I worked for a general contractor for about 8 or 15 years, and then I've been with the campus here for 5 years. And as part of my job here on campus, I help oversee getting plans from the paper design built. So it's managing the construction procurement process, the contractors, our project managers, schedule, and budgets.
So today we're going to talk about some of the clean energy, battery storage, and so on project we have going on. We have a lot of other stuff. We have about over $100 million worth of capital projects active at the moment, either coming, going, or in progress. You've probably seen the guys out on the roads pulling wires and causing all sorts of a kerfuffle. But we're going to focus in on 3 projects today, and I'm going to give you a little bit of a background in terms of how we got to these 3 projects, because there's a lot more to what we do than you would think. There's a tremendous amount of planning involved to get us to the point where we can have a capital project or that we do capital projects that can fulfill multiple objectives. There's a lot of complexity in a university campus, which can make it kind of fun. So as I mentioned, I'm going to talk about how we got here, integrated planning in higher education, the campus's strategic plan, our clean energy master plan. We were one of the first campuses in SUNY to complete a clean energy master plan, and I'll get to that a little bit more. I'll speak about SUNY's climate action plan. I don't know if you've heard that. SUNY's recently released its climate action plan, as well as the campus facilities master plan. Now, all of these plans have to be integrated to form a kind of cohesive capital program. And that's the point where all those ideas go to Cindy, where she actually has to make reality out of all of that. So we're going to talk about our underground electrical upgrade project, which we're nerds, so that's pretty cool for us. A solar power purchase agreement, which is essentially, we're going to build a 1.2 megawatt solar array on campus, and that starts construction next summer. And a Department of Energy battery storage grant, so that'll be in either 27 or 28, where we'll construct a large-scale battery storage system here on campus, and it'll all be viewable and accessible by faculty and staff and students. So just a little bit on higher education integrated planning. It supports strategic decision-making. It provides a comprehensive view of resources and commitments, and aligns financial and capital resources. So on campus, there's a lot of plans. We have ADA accessibility, clean energy master plan. We try to integrate academic plans and the facilities needs, residence life, renovation of res halls, sustainability, life cycle asset management, which is a critical maintenance stuff, parking studies, classroom utilization, climate resiliency. We have to plan for these extreme weather events by having flood mitigation and emergency generation resources, as well as the clean energy master plan that I mentioned. And we are very much affected by external regulations and state mandates. All sorts of state laws coming out about decarbonization and climate protection. So to the campus's strategic plan, there's a couple of items in the campus's strategic plan that speak to this kind of work that we're doing. And the first one is that SUNY Oneonta will clearly be an institution that visibly prioritizes climate stewardship and decarbonization via academic programs, scholarly commitment, operational programs, and facility development. So that last part is part of what we're going to talk about today. Then item 13 in our campus strategic plan is SUNY Oneonta will have a physical plan that draws students, facilitates academic excellence, accelerates engagement, promotes efficiency, and fosters climate stewardship. So we're going to have a good campus facilities. So as well as the campus's strategic plan, we have our own facilities master plan. And that had a series of planning principles. I'm going to get into a bit more detail about the facilities master plan. And that was really put together between like 2019 and 2022. And there were a lot of campus participants took part in the facilities master planning process. So it was the work of many people. So one of the planning principles is to integrate energy efficiency and long-term carbon reduction strategies. So as I mentioned, we completed a clean energy master plan in 2020, and it really is a toolkit. It's more descriptive than prescriptive, but it's a toolkit for decarbonizing this campus. And by decarbonizing, I mean scope 1 and 2 emissions, which are purchased energy, and the energy, essentially the energy that we use, the heating plant, and the energy we consume in our buildings on a day-to-day basis to run these facilities. So the objectives were to integrate with what we're doing with our facilities master plan, meet or exceed some requirements, greenhouse gas reduction requirements of SUNY, reduce our fossil use and our dependence on gas, increase use of renewable energy, upgrade infrastructure for future loads, which Cindy will speak to with this underground electrical project, increase climate resiliency. And there are a number of recommendations, and the Clean Energy Master Plan, it's a very long-term plan. So it's not, it reaches all the way out to 2045. So the plan is a roadmap for how we can reduce our carbon emissions by 85% by 2045. It's just quite a long reach, but there's a lot of money and a lot of capital investment required to do that. So probably in today's dollars, probably $300 million to decarbonize this campus in today's dollars. So apart from the fact that that's a lot of money to get all at once, we can't shut down the business of the university, which is educating students, just to do that. So this whole thing will be phased over a period of time. So some of the distributions was to get rid of our steam heating systems and transition to a low temp hot water distribution system. Establish geothermal arrays. We already are operating one of those at Alumni Hall at the moment. We're about to build another geothermal array when we renovate Netzer, which starts next year. And the long-term plan is to have a bunch of these geothermal energy arrays in nodes around campus that will be linked by a low temp hot water network. Behind meter, in front of the meter solar, through these things called PPAs. PPAs are interesting means of getting solar arrays built, because you don't have to come up with capital money to construct a $2 million solar array. You just say to the developer, come in and build my 1.2 megawatt array, and I will pay you a fixed price for energy on the basis of that for the next 25 to 30 years. So it's a way of financing some of these projects through utilities purchase. And we're always doing deep energy retrofits of buildings. We completed one at Alumni. We are about to start one on the renovation of Netzer Hall. We always are able to achieve some significant energy efficiency savings through the renovation process. Fortunately, those are also very expensive projects. We can see ourselves maintaining the central plant. It's in good shape. It's probably got another 20 or 30 years life in it, but it will reduce in its importance over time as we start to become more electrified with other buildings, and it may transition to a biofuel basis for peaking. So I mentioned before, there's a lot of external drivers on what we do. There's a thing called the Climate Leadership and Community Protection Act. That's a state law that requires us to reduce greenhouse gases. There was a sustainability executive order issued in 2022 that has a range of sustainability requirements of state agencies. Amongst that is greenhouse gas reductions, focus on energy improvements, renewable energy adoption. There's also a thing called Build Smart 25, which is energy efficiency reductions. So we have a lot of inputs externally from various regulations and laws. There's also some interesting regional issues here, and I don't know if you're aware of this, but this area is natural gas constrained. So there is a pipeline which comes to Oneonta from the main pipeline called the DeRuyter Spur. It's very old. It's old and small and not in great shape. So that pipeline constrains our ability to increase the use of natural gas in this area and puts pressure on the utility. So what we find here is, because we're a dual fuel campus, if there's a really, really cold night, which happens quite often, the gas company will come to us and say, we can't give you any more gas, because they've run out. So we have to switch to burning fuel oil, which is arguable. What is the better? But there are a lot of cold nights when we're burning fuel oil over there in the central plant versus natural gas, and that's 3-4 times the cost. And in terms of local emissions, that's a worse situation. You can make an argument that natural gas comes from frac sources and there's methane release in that process. We could argue about that all day long. But the fact is, this area is natural gas constrained. It's also constrained by our electrical transmission grid to the campus. So the grid to Oneana to this area is largely built out. It doesn't have a lot more capacity in it. So there's limitations to how much more electrical power we can require from the grid. There's also limitations to the natural gas side of things. So it's an interesting spot to be in. So I don't know if you've seen any of the news, but SUNY's recently released its SUNY Climate Action Plan. And I sort of like ripped from the headlines there. It's a big, thick plan. There's a lot of different initiatives in it, but with respect to what we're talking about here, we're reducing greenhouse gas emissions, developing innovative technology and commercialization to scale, such as demonstration technology projects, careers in climate sustainability, conversion to renewable energy, and there are certain megawatt hours targets. And our solar array is about 1,600 megawatt hours per year. So that's a little piece of that 66,000 megawatt hour objective for renewable energy. Empower students, faculty, and staff and communities to achieve those climate goals. So that is another input to what we have to kind of manage. So sort of back to the facilities master plan. The master plan called for a whole bunch of projects, and a lot of those projects that are highlighted are related to sustainability, energy use reduction, renewable energy, climate resiliency, such as drainage mitigation, EV charging, emergency generation. So this whole area of energy and emissions reduction and climate resiliency is a big driver to what we do. So this is our facility. By the way, our facilities master plan is available on the SUNY Oneana website. If you care to peruse that, it is a 10-year outlook to development facilities. Of course, it's all predicated on funding. So we can't exactly predict what capital funding we can get, but it does give us a roadmap for where we're going. But once again, you can see some of these projects here are, related to climate sustainability, electrical infrastructure, substations, solar arrays, sustainability improvements, resiliency upgrades. So I'm going to hand over to Cindy. She's going to talk about an infrastructure project which we're currently building, and you'll see all those folks out there working on it.
Thanks, Lachlan. So I'm going to talk about the underground electric project. So the overall budget for the project is $24 million. The construction started this past summer and it's ongoing. Like Lachlan said, probably you saw today, they were on Ravine Parkway working, and they were over by MOC a couple weeks ago digging some of these trenches on near West Street for some of the new underground duct bank and cabling. So this project will prepare our campus for future increased electrification associated with decarbonizing our buildings as we add more electric equipment, such as ground source heat pumps and air source heat pumps, and get away from fossil fuel powered equipment. The lead time on the electric equipment is approximately 10 months. And so that's been ordered, and that's all coming in April. We started this project back in 2021 with an initial electrical study. We hired an electrical engineering consulting firm to kind of evaluate what our existing conditions were and look at the future electrification of the campus to see where we had to be and what we had to do, and gave us a plan how to get there. So after that study, then we did a design, and it's a design build contract, and it's actually that's one style of a procurement method with construction contracts. So usually it's design bid build, right? Contractors bid on the job, it's low bid, but this design build, it's different. We're working like it's where the designer and the builder work together as a partner. So it's one of the first, we're the first campus in SUNY to have a design build project. So that's another first for us. This project is scheduled to complete in 2027. So all in, it's about 6 years, and $24 million is a big price tag, and it requires a lot of coordination with electrical shutdowns and building, and we are doing this all to make sure that, we don't impact, business continuity, your classes, and keeping everything running like normal.
Just a quick question.
Yep.
What were the big drivers of electrification that
Right.
required this?
Right, so all the, so we're trying to get away from fossil fuel powered equipment. And so now we're installing things like heat pumps that are 100% electric. And as we add more heat pumps, that requires more power from the grid. That's an
the
example.
biggest one.
Yeah,
Yeah.
right. So we have a plan on our clean energy master plan. There's going to be, Lachlan was talking about, we have a central heating plant, but then we're doing other districts like we did. Alumni Hall has a geothermal district, and if you go in that mechanical room, there's all kinds of heat pumps in there. And we're going to, at Netzer, that's going to probably go under rehab in the next 6 months to a year. That's going to have another geothermal ground source installation. So there's all this equipment that we had to evaluate. What's the load? How much power does each piece of equipment take? They've evaluated every building.
So the existing cabling out there is about 35 years old.
That's not the slide.
Sorry.
So,
I'll go for your next slide.
oh, no, the previous slide.
Okay.
So we're putting in, this is all the quantities, 25 new transformers, 26 new switches, 5,000 new feet of duct bank, and 150,000 linear feet of new electric cable. So we're going to be starting that in the fall. So first, so in red here, this is the new duct bank we did, but we're not showing all the existing, that's probably it, like all the existing duct bank. So in all the existing duct bank, we have to pull out all that cabling and replace it. And we have to keep the power onto each building, right? So the primary electric here is being replaced. It includes replacing the transformers, and now they're going to be replaced with something called a dual tap transformer. So I'm going to get into that a little bit. Right now, everything's operating at 4,800 volts. With the future electrification and the future demand, we're going to need to have 15 kV. So this transformer that we're putting in, the existing transformers are near the end of the useful life. So when we replace them, we're setting them up ourselves up for the future so they can operate at the current voltage or at the future voltage. So in addition to the transformers being rated for the higher voltage, all that cabling is going to be rated for the 15 kV, and it's also nearing the end of its useful life. So our operations department does a really great job of maintaining all of our equipment, and so we're being proactive in replacing this before we have a failure. So we have a testing program in place. It's usually after you guys leave. It's the day after commencement. The campus goes dark and we test everything. So this is the first of two major electrical projects to prepare us for decarbonization. The second project will require us replacing our substation to accept the higher voltage. And I'm going to go over that in a few slides. More quantities for this project. There's complex rigging with like cranes and equipment handling. The gear is heavy, getting it in and out of buildings. Sometimes we might have to cut out holes in the building to get it in and out. Then some of our buildings are older and they have asbestos, so we have to work with the asbestos, abating that. And then there's restoration to roads, sidewalk, landscaping restoration. Next slide. So as we plan for the electrification of our campus, we had to coordinate with our utility supplier, NYSEG, to confirm that they can meet our future needs. This also required us to work with that electrical engineer to help us forecast our future demand load. That's why we did that electrical study. So as we retrofit our buildings or we do gut rehabs, we try to install more electric equipment, such as those air source heat pumps. We just put that in at Perna Science, and then ground source heat pumps, Alumni Hall and Netzer in the future. So we don't rely on fossil fuels anymore, and it helps us with our decarbonization goals. So another factor, we're not the only Hartwick or the hospital, Bassett. There's other people in the area who are also electrifying. Homeowners themselves, right? These houses, they're all like, there's new New York state laws where you place your boiler, you have to go with an electric boiler. So all these different groups are all putting a larger load on NYSEG, not just us. So we have to be cognizant of that. So our renewable energy project with both the solar and battery that we're going to get into shortly will give us more flexibility to not be so dependent on the grid. And during peak periods, we can load shed and put less strain on the utility supplier and make it available to other customers in our area. So this is our existing substation. Oh, I have one more thing on my last slide. So we talked about NYSERDA. So going to electric means greener because the electricity in the upstate New York grid comes from renewable sources such as hydro, wind, and solar. And so New York State's electric grid is 70% renewable by 2030 and should be 100% renewable by 2040. So we get away from fossil fuels, we go to electricity, but it's better because that electricity comes from those renewable sources. So this is our substation. Our substation has 3 transformers here. This is West Street, the president's house is over here. There's a tennis court parking lot. So how a transformer works, the power comes in from the utility at 46,000 volts. That's high voltage. And what a transformer does is it steps it down. So at this level, it steps it down to medium voltage, which is 4,800 volts. And then it goes into each building, and each building has an electric room, and then another transformer steps it down to what you plug into, right? Like you're used to 12208, that's low voltage. And there's different trades, different electricians are certified. They only work, you wouldn't want a low voltage electrician working on high voltage, right? The risk and the safety, there's a lot more involved.
Sorry to interrupt again, but there are actually a lot of careers in high voltage.
Yeah.
Electric work.
Yes.
Seems like totally separate.
So our campus is a radial system with 5 feeders. There's 2 redundant feeds at each building. So this is like there's bus 100, 200, and 300. So 2 feeds come out of this one, 2 out of this one, and I don't know why one only has 1. So we have 5 feeds that come out, and then into each building you would have a combination. You might have 201 and 301. And if there was a problem, and the building's only operating off of 1 feed, and in each electric room, there's a switch where you turn on, like, okay, I'm operating on 201 and 301's off. So with a lot of campus systems with mechanical, electrical, the redundancy, because if you need to do maintenance on one, or if you have a failure on one, you have your backup. So that's how our campus feeder system and substation works. So as our campus electrifies, our electric study in 2021 shows that we'll need to replace our substation in about 10 years. So you have to keep the existing substation working, build a new substation, and then transfer it over, and all while trying to keep the power. There might be brief shutdowns, then you might have temporary generators, but it's a lot to actually logistics. There's lots of logistics involved in all of this. Next slide. So this is an interesting slide. So this is a chart, and it shows with different scenarios. There's like, if we had our heating plant, we got rid of our boilers, and we had a combination of ground source heat pumps and air source heat pumps. When the capacity or when the demand's the highest on campus, like that's the peak load that we require to operate the campus, right? Scenario 1A, 2A, 2B, and 4 all are that they're all fully electric, right? But this is the max we can get. This is the max supply we get. So we can only technically do 1B with what power we can get from the substation. And it's not fully electric. It's a combination. We're using ground source heat pumps, air source heat pumps, and then we use natural gas for peaking. So if it's like a really cold day and there's a lot, a lot of need for power. So we might need to have one of those natural gas boilers to back us up on those super cold days.
So this, you can expand this to New York State. So if New York State was fully electrified, you know, what we're talking about with heat pumps and ground source heat pumps, and we get off consumption, we go to electric and we get off heat through fossil fuel, it would at least double the amount of energy used. So for our campus, our absolute peak is 5 megawatts currently. We do that in September when the students come back. And in February, our peak is about 1.62 megawatts. So some of these scenarios with full electrification, we're talking 18 megawatts of power required
3 to 4 times.
to fully electrify.
Whoa.
So there's an interesting debate going on in engineering circles at the moment about you can reduce 85% of your emissions with about 60% electrification. And it's like the 80-20 rule. So that other piece of it is going to take a tremendous amount more power and a tremendous amount more capital money and equipment. So it may be that the sweet spot is reducing emissions by 85%, which would still be a tremendous victory. But it's this could be what we're looking at in the future. Could be the great being the enemy of the good. So this is going to be, the next few years going to be very interesting. We're just starting to hear this conversation. 5 years ago, full electrification, and now people are saying, whoa, you know, just the embodied carbon in all of that, you double your equipment to get 15% emissions reduction. How much embodied carbon is there in just building that equipment? How much more power? Can the grid handle this? So this graph's actually really telling.
But that includes a life cycle analysis, essentially.
How much carbon has to be consumed to construct all this additional equipment to get that extra 15%? And then we may be looking at a situation of diminishing returns.
And another way to look at it is, would you rather have one building net zero, carbon neutral, or would you rather take that extra money you could have spent to get that extra 10%, put that into 2 more buildings, and you have 3 buildings that are maybe 85% reduction in the carbon?
Yeah, this is not a good conversation for purists.
Right.
It sounds like a calculus problem. Calc 1 people doing minimization, maximization.
Some point, I did.
I think you have to hit like a couple. I'm just going to show all of them.
Okay.
I think that's it. Okay, so now I'm going to talk about our planned solar projects. We started back in 2023, and we're working with the New York Power Authority on this project. So we are doing the procurement with them, and then we hire a developer to do that PPA. I'll kind of explain the PPA. Lachlan touched on it a little bit. So we started it in 2023. The request for proposal went public in 2024. We advertised, a couple of different developers submitted their qualifications. We reviewed their packages, and then we select the most qualified developer. We did interviews. We had some procurement challenges. So that's another obstacle with New York State. There's all kinds of procurement rules. So we had some legal procurement issues. So we had to kind of regroup and go back and reselect the developer. So we've done that. We have our design, our site plan pretty much ready to go, and we're going to be and we're doing our internal permitting process right now. And we're going to be in construction next summer. So PPA. So a PPA is a purchase power agreement. It's a financing agreement where a third-party developer owns, operates, and maintains a solar system on your property, and you, the host customer, pay for only one or for the electricity it generates at a fixed rate. PPAs provide significant benefits like no upfront costs, lower monthly electric bills, and a reduced carbon footprint. However, you don't own the system, and the rate for electricity may increase slightly over the terms agreement. And they range from 15 to 25 years, and I believe ours is about 25 years. So benefits, no upfront costs, fixed energy costs. They handle all the maintenance, and it's environmentally friendly. And at the end of the useful life, you can extend the contract, or they decommission the solar array for you.
So are we going to be paying for this power, but at a reduced cost, or?
Yeah, we'll pay for the power at an increased rate. However, we won't have to come up with a couple of $1 million to build the. Yeah, so there's an economic analysis over time
Okay.
where you look at, what's the break-even point, and the break-even point for us is like 12 to 15 years out.
Yeah.
But over a 25 to 30 years period, there's a net present value. There's a positive net present value. It's not a huge economic. It's not a huge economic benefit. Part of the problem is that we get power currently so cheaply through a consortium, like a buying consortium. Through SUNY, we get power for about 5 cents a kilowatt hour, which is ridiculously cheap, and that makes the simple economics, a lot of these energy projects, hard to make simple paybacks work. However, I would have to say that's a fixed rate over 25 years. So I think the chance of volatility in future power cost is high. So the payback may be a lot quicker than we currently project.
And another reason why we are really interested in doing this solar array is this is behind the meter, right? So all the power, because sometimes with solar arrays, you can send power back to the grid. But we're keeping all that for ourselves. And if we have a power outage, it's going to be tied in. I was talking about those feeders from the substation. So this solar array is going to be tied into the electric feeder that goes to the most buildings, res halls, so that we can provide some of the basic electrical, like keep the building warm, life safety on for a few days.
And that would work with battery storage, in combination with battery storage.
Right. So this is our planned solar development. This is the president's house. This is the MLC. This is the tennis court parking lots, just so you can get an orientation. So this is, it's going to generate 1.2 megawatts of capacity for us. And that's basically 7 acres. So a year or so ago, we didn't own this land. I don't know if you know Job Corps. They're the adjacent property owner, and they're operated by the New York State Office of General Services. So you can transfer land between two state agencies. It was kind of a challenging process. It took Lachlan a year with all the attorneys to get that land transferred to us. But so we use 3 megawatts a day typically on campus, and so this will supply about roughly a third of that. But you need this square footage, right? People always wonder, like, well, why aren't you putting solar panels on the roofs? You see that a lot of places, right? So another thing that comes out, like, so you could have them on so many roofs, right? But I bet you, I don't think we would come up with 7 acres worth. So, I mean, it might be able to feed some needs, but then additionally, you have to think about the replacement life of the roofs, right? Why would you put a solar array on here that's going to last for 25 years when the roof has to be replaced in 5 years? There's different things to consider.
So just as a little bit of a sense of this, that's about 7 or 8% of what we would require to generate enough for the whole year. That because of the lack of efficiency of solar in the winter, the total generating capacity of that is about 1,600, 1.6 megawatt hours. We typically use about 24 megawatt hours a year, so it's like 7%. So that's 6-7 acres. So you can get a sense of how much acreage we would need to create sufficient generating capacity for the campus, not to mention the storage that would be required.
So this site, in addition to the solar, right here, we're doing that battery demonstration project. Sometimes they call that a long duration energy storage. So the combination of the solar and the battery is going to have a transformer and a switch that's going to have underground cabling that goes back to the campus substation to help us during an outage, or, you know, just to shave what we're using every day. So Lachlan's going to talk more about the batteries.
Okay. So the battery storage project is going to be really cool. This is, you get a sense of what this is going to look like. It's going to be a significant kind of installation. It's actually, there'll be sufficient battery storage for 3 megawatt hours. And this is a demonstration technology project. So this is the New York State firm, which I'll get to in a little bit, that has got a new technology. It is non-lithium, it's non-rare earth. All the materials are readily available in the United States. It doesn't catch fire. So there's a tremendous amount of advantages here. So we're working with a group, a consortium, New York Power Authority, ourselves as a host, and Urban Electric Power Corporation, and the Department of Energy Office of Clean Energy Demonstrations. So they give out grants for companies to scale up from prototypes to commercialized size, which is what this project is going to be. The grant for us is $6.17 million. We're hosting. It doesn't cost us, it's not going to cost us anything. They're going to come in and build this equipment here and use it as a test bed for larger scale commercialization of the technology. So there were not a tremendous amount of awards across the US. You can sort of see, you know, where some of these grants were awarded. And our project is in conjunction with Westchester County. So where we are at the moment is the award for this particular campus is $6.17 million. That's what the installation will cost. We are in the process of completing the detailed work plan and getting into project development. And we expect to be in construction with this demonstration technology project in 27 or 28. So the company that we are partnering with to host this project is called Urban Electric Power. They're kind of an up and coming New York State firm. Their technology is rechargeable zinc manganese dioxide batteries. So kind of like a massive ever-ready battery on a very, very large scale. Obviously, they've got some proprietary technology and chemistry to allow these batteries to be rechargeable and long discharge.
Please, can I add something?
Yes.
So Urban Electric Power started as a research project at CUNY in the city. So it was a research project with grad level students that turned into a business.
Yeah, now they have a startup. So they were probably physics students.
Yeah, I've been more and more as job market is tough, I've been collecting companies. And so you guys should do the same. You see an interesting company and right, because if you're looking on Indeed these days, I'm sorry, Mike, this is bad. Indeed is 90% fraudulent. If you know a company, go right to it. And I saw one today. I went to the company, and all of a sudden there was a little Oneonta badge, and someone from Oneonta works at this company. Indian, I think, is semiconductor electronics just south of you. But anyhow, so collecting companies is a good idea.
So what we're starting to build a great relationship with this company. They're going to be here. They're going to be working and building this installation, and hopefully we can form the kind of relationship where we can have students do internships and try to integrate this technology, demonstration technology to curriculum. So the idea of the battery installation is 300 kilowatts. It can discharge for 12 hours. So it's long discharge. a round trip efficiency of at least 80%, low losses, and also the ability to operate with some efficiency reductions in low temperatures like -10°C.
One question, Lachlan.
Yes.
I think another, do I remember correctly, another advantage of these is they, like lead acid, they're almost 100% recycled.
Yeah, they are. Yeah, and also non-hazardous.
Yeah.
You don't end up with hazardous chemicals at the end of it. And there are some, I've got another slide with some of those advantages coming up. So it's the same chemistry as a traditional AA battery, engineered for power resilience. And you can sort of see a little exploded view of the construction of this with a manganese and zinc electrode. I'm sure that they have proprietary features, as I mentioned before, that is going to give them advantage. It's actually a safe installation. There's a lot of concerns about lithium batteries catching fire, particularly if they've been subject to abuse or there's been a hole in it. This battery technology doesn't have a risk of thermal runaway, so you don't see any spectacular fires. And hydrogen is the primary gassing project. Lithium-based batteries can create toxic chlorine gas, hydrofluoric acid, and phosphoryl chloride. So the technology is safer. The minerals are abundant and readily available in the United States. We don't have any sort of concerns about where these minerals are being mined and under what conditions and who's being forced to do the mining, because there are some concerns about lithium battery technology that way, as well as safe handling disposal. They're safe for disposable through traditional waste streams and fully recyclable. So they're going to look like these cabinets, which, if you're around in a couple of years to see this installation, you'll see it'll be a fencing gravel pad with about 30 of these freestanding cabinets. The company has already deployed some batteries in this technology at a smaller scale. And you can see some examples of that. So I'm going to hand back to Cindy, and we can kind of bring it back to these projects.
Sure. So we kind of touched on 3 of our key projects today. Our infrastructure upgrades with our transformer and cabling replacement, and then talking about the future substation replacement. We talked about our renewable energy projects with the battery and solar. We touched a little bit on the peak load reduction. And Lachlan, in the beginning, he talked about our facilities master plan, clean energy master plan, and some of the mandates we have for climate resiliency. We didn't really touch much on this. So I wanted to talk a minute here about this demonstration technology workforce development. This is in the concept phase, but when I was showing you that site plan where the solar and batteries go, there's also going to hopefully, if they can get funding or maybe some grants, be a workforce development center there, because all these technologies new to our trades, right? In the workforce, and they need to be trained on it and how to operate it and for their career paths. So if we have this building there, they can, do some work with solar, they can do some work with the batteries. We might be able to have that building itself could have a heat pump technology there. So there's a good opportunity there. Because all these systems are a complex system, it's very technical. So sometimes the trades get a bad rap, but it's complex and it's technical, and it's really important to have the people to work on these systems for us. Because right now we have some challenges with our new air source heat pump. Some of our heat pump installation, it's a complex system. So there's control, so there's computer, there's programming, and the service tech we rely on comes down from Buffalo. That's the closest one to us. So it's really important as all these different people go to these technologies that people know how to operate and work on these. So I'm going to wrap up. As you can see, we have a lot in the works and facilities to better the campus. A lot of planning goes into executing these plans and making it a reality. So I think the takeaway for you guys, are there any people, businesses, or organizations you can partner with on a project you wanted to do or a company you wanted to learn more about? So we partnered with NIPA and the DOE, so there's always opportunities out there. You just gotta go find them.
So I'm going to leave this slide up. I had a really cool slide here with lots of question marks, but I'm going to leave this slide up because that actually prompts some questions. But you know, what our projects, what I'm looking for is 2 firsts or 3 firsts. So whenever we do a capital project, we try to achieve multiple objectives. So we talked about 3 projects, but really these projects are addressing a range of issues, and that's kind of what we sort of see here.
So there's 32 SUNY campuses. There's 64. Half of them are community colleges, but there's 32 campuses. There's so many comprehensive, that's our size. And there's the 4 university centers, and we're all fighting. Like, we get so much money a year allotted to us, but then we have to like submit a project and have it scored, and we're all fighting for that same pot of money, and we all have the same objectives here. So the more we can fit into one project, the bigger bang for our buck, and hopefully we, get the projects.
Any questions?
Okay, so
There's a lot, isn't there?
it is a lot. It's cool. A lot to digest. So right now, because Dr. Lapson's going first, she's giving you a read for you. Everybody should be able to come up with one interesting or straightforward question. Could be something there. I have 12. But anyway.
Hopefully mine will prompt more questions, but my question is, especially once we get the batteries and the solar panels and stuff up on campus, is there any way for our students or students on campus to work with you to maybe study how much energy are we getting? Is the battery storage actually working? Like, can we coexist and do some cool student projects to help them watch all of this happen?
That's exactly what we want to do. And I think the demonstration technology project is interesting. There's a research paper opportunity there to work with the company. We want to leverage this in opportunities for internships, applied learning. So we're very, very conscious of that.
And envision in smaller scales, but you can envision measuring light in the field around the solar array. Yes, you can predict it by various models, but actually measuring there, so you know the energy that's input. And then these panels are going to produce an output that they use a charge controller at some point.
Yeah, they have an inverter charge controller.
Okay,
Yeah,
so,
and they'll convert that DC into 480 volts AC.
yeah.
But we'll have that'll all be computer monitored, so you'll be able to read the output of all of that.
Right, so those are interesting to look at because there were efficiencies in that, in some of those processes that I know people are working on. To see them, and then charge times and discharge times of batteries, configurations of array, you guys did lots of resistors in parallel and series. All these are, sources in parallel with series. The solar panels are a little different than current sources, voltage sources in general, but I think a lot of watching and evaluating.
Yeah, and as Cindy mentioned, that we've reserved space on the land to construct a lab building. So should we be able to get sufficient funding together, the vision is that will be a lab building where students will be able to go to and either monitor or work with that technology or down the track a little bit.
Or as we replace, like in a specific building, say we replace a piece of equipment with that has a higher power draw, you can analyze before and after what are the benefits or what's going on with that.
This is a question I had. We have a heat pump building with a geothermal contact. How do you know how effective? Have you seen a decrease in your oil and gas use?
Yes. Well, all our buildings are sub-needed, so we're able to measure before and after. Yes.
Okay. So that-
So the before energy use intensity of Alumni Hall is like 100, which is kBTU per square foot over a year. It was it's like the average energy use was like 110, 120 estimated at, and now it's less than half of that in
Yeah.
terms of its absolute energy use. So that the heat pump system is it's very efficient, but it's still more load on the electrical side than if
Right,
we're just producing heat with burning oil or gas.
right.
But that's all measurable. We have sub-metering. So over time, we can kind of confirm that. And then we can also understand what the scope 1 and 2 greenhouse gas emissions reduction is as a result of the project. But it's a little less easier because it's one building of 44. It's a little more difficult to measure that reduction in fossil fuel consumption because you got so much seasonal variability. It's hard to, that's kind of noise in a way. It's when we get 5, 6, 7, 8, 10 buildings,
Yeah.
then it'll be a significant
Well,
reduction.
not knowing that you had the sub-metering, that was my concern, but.
Yeah.
Okay, I'm talking too much. Who's got a question?
So I don't know if you already answered this, but so between the lithium batteries and the zinc batteries, so are they like, is there a difference in efficiency? Like, I see that the zinc ones are a lot better for like general stuff like safety, but are they just as efficient or less efficient?
So, to be just as, so the con of the alkaline batteries is they take up a larger footprint to be just as efficient as their counterpart. So, but there's so many more pros, but you
Yeah.
need a larger footprint to be just as efficient as the lithium batteries.
And then there's also some geopolitical issues about rare earth minerals and where they come from and which countries control that supply and who's mining that and under what conditions. So it's kind of pros and cons. So
Yeah, I do have a counter question to that, what you just said. So do you think that the emissions given up by just like getting those rare metals is actually like, how do I word this? I'm sorry, I'm trying to think of how this.
the embodied energy, I think
Yeah.
you're getting at what
Yeah.
you're getting at. And I actually think and I'm glad you asked the question because I need to go and research that. But I think that constructing lithium batteries requires more embodied energy than this technology. But that is a really excellent question. I'd like to
Well, and
understand the specifics of that.
and there's a second aspect to it. That would fit in embodied energy, but with the lithium being difficult to recycle and lead acid batteries, for example, not, then you recover the material and you don't have to mine it, right? So, if you, what's your name?
Landon.
Landon, I'm sorry, I don't know you yet, but if you send me something out of a couple, a neat consideration of this is electric vehicles. And I'm super glad that you talked about how clean the upstate grid is. Doing this electrification in Utah would not be a benefit in general. But I have some slides in an article on embodied energy, gasoline car, hybrid car, electrical car, and it goes through every step. And does address things that might show up in some things like this too. Electric cars are more expensive and more energy intensive to manufacture. They do need less repairs, which is an energy subtraction. If your grid is good, then you get some points for that.
Yeah.
And it's not a silly question.
So,
It's an excellent question. And I think all of this is a huge exercise in critical thinking and
Yeah.
just understanding what the inputs are. For instance, lithium, you got to ship that from another country. It's probably refined somewhere else and the resource is not as recoverable afterwards. That would be an excellent paper to look at.
Yeah.
What are you gonna say?
So on our construction contracts over $1 million in value, now one of the requirements from student sustainability is to track embodied carbons on materials over, there's different parameters like steel over like 1,000 pounds, concrete over so many cubic yards. So we're trying to track, right now we're just starting to track embodied carbon, but then we might start trying to improve on, how much embodied carbon we're producing in the future. So just now we're starting to track it, but I'm sure as time goes on, we'll try to start reducing our embodied carbon.
And some of our projects, well, our consultants have proposed energy reduction measures to us. We've said, okay, how much is that going to cost? And how many pounds of carbon reduction emissions is that going to reduce through the course of the year? And then how much embodied carbon did it take to make it? So there's a whole different cost benefit analysis nowadays than there ever was before, where it was like, how much is it going to cost and how much will I save? Now it's more of consideration of, if I want to invest $1 million, how much carbon emission reduction can I get out of that? And sometimes the emission reduction is more important than actually the efficiency.
Right. It's more important to save the environment versus breaking even and turning a profit.
So this is where you get to different types of analysis, but life cycle analysis, and we should also be life cycle engineering, which is,
Really great.
yeah, I look at the cost of nuclear, but an old nuclear power plant just came offline in Connecticut. I think it was one of the first ones, and they had nothing in the cost of the electricity they produced accounted for the fact that someone's going to have to manage this plant past its lifetime. Right? Two more you questions, so I will talk. So go ahead, Jack. I do want to talk something. They're going to be ready.
I have a few questions. For the geothermal heating, how deep do you have to, like, on average, dig into the ground?
Alumni is 500, 499. It's interesting, funny story, because at the time when we drilled the wells for alumni, if you went below 500, you had to have a mining permit per well. So we did like 36 or 39 wells. So we would have had to have 39 mining permits. We would have been like major mining magnates. Could have gone to mining conferences, and so there was a kind of a bureaucratic problem there that caused everyone to drill to just less than 500. That's still since been eliminated, and where we did our test well for NANSA went down to 660, 700 feet per well, and it's a loop that goes down the ground. But there's a break even with that as well, because the deeper you go, the more expensive it costs per linear foot. And you have to balance that up with the amount of available real estate, because shallow wells, more real estate, they've got to be spaced apart.
So if you're ever in between Netzer and Chase and you see that random cable coming out with that wood post and you're like, what the heck is it? That was our test station.
And so water's down there. And what's its temperature?
In the 50s, 50 degrees.
So,
yes.
So like how cabbage?
Yeah. And it's mainly the conductivity of the rock strata more so than the water. So that's when you're circulating in the summer, you're pushing that heat down into the rock strata where essentially it stays. And then in the winter, you're pulling that out. But with these geothermal systems, you have to be very careful to balance those fields. Can't be all pulling the heat out or putting the heat back in, because eventually you start to lose efficiency.
Jack, so they talked about it too. They talked about the subsurface systems and also the surface systems. So they can be designed. They don't need to.
Correct.
But having that nice reservoir makes them much more efficient.
And the technology is always improving. Like maybe 5-10 years ago, we wouldn't have put an air source heat pump on Perna, but now we did. And maybe there's in the future, we'll do it in more buildings. Because the thing about the ground source heat pumps is you need the area to drill all those wells.
And if you've ever looked at an underground utility map at this campus, you realize why that's a problem,
Right.
because it is an absolute mess. Well, that's maybe not the word I would use, but there's a lot of underground utilities and there's not a lot of available space to build wells.
Aiden,
I was gonna ask, in comparison to the solar systems you guys are setting up, how efficient is, or are the heat pumps? And, like, how much?
Well, different technology, because the heat pump system, a solar system generates energy, sun to electrical energy. The whole objective of the heat pump system is like leverage. So using a small amount of electricity through the efficiency of the heat pump system to generate a lot of heat. So for example, if you use an electric radiator, you can produce 100 watts of heat with a given amount of electricity. But if you've got a heat pump, that has a coefficient of efficiency of 4 or 5. So instead of 100 watts of electricity in, you can get 400 or 500 watts of effective heating. So the heat pump system is more like a lever where you're turning a small amount of electricity into a lot of heat or a lot of cooling, where the solar system is just generating.
putting you in the spot or judging you. We had someone come and talk about heat pumps last night. I think you were here. Yeah. No, it's fair. I can't remember either, but it was, the instructor for the heat pump courses at Delhi is studying on physics a lot.
Oh, wow.
And he came back and talked.
I think part of the problem is it's often referred to as geothermal energy. And that is confusing because you have geothermal energy in places like Iceland where you're drilling deep bores into hot stratum, then you're really generating electrical energy from that.
Mm-hmm.
But the geothermal system is really ground source heat pump.
Those heat pumps are water to water heat pumps because it's the water from the earth, water, so it's the water to water, whereas like you have air to water from the air source heat pump.
You use that 58 degrees or whatever it is, it brings you up to 58, you get a nice reservoir, and then you basically run a refrigerator backwards and exit it into the home. Whereas you're right, it's a misnomer. I always refer to that as geothermal, but I think when we're really talking about geothermal, it's Iceland or Kenya. Cornell's
gone ultra deep. They've gone like 10,000 feet or something.
And that's brand new, isn't it?
Deep bore, where that's a different technology again.
So they can be called, we call them thermal energy networks because it could be the water to water from the ground, the air, or you can put in storage, and then there's hot water storage, but you can also have ice storage. So that's different technologies, all the storage up here.
But the objective of TENS is to link all these things.
Muhlenberg's thermal class is getting more important with every. It always was, but. All right. Go ahead, Michael. Michael, are you the senior person here?
Look, I guess, I mean, you're here.
There goes the grade.
So my question is, and I'm not saying that this is any reason you would do this, but was there any reason why you went with like solar versus going for wind power or some other?
So we do have identified a couple locations where we could put a turbine, a wind turbine. Just this opportunity, and they have different programs already available to us. So we do have that. We could do that in the future.
So I think that that market for large scale solar development and TPAs as a financing tool is more developed than doing the same thing with wind. But that ultimately that'll come along.
Would you be willing to share the locations you've identified? Because myself and Chris Karmofsky and 2 other students went through a state-of-the-art, a training on a state-of-the-art
wind planning software tool. Might be good to sort of, might be fun to duplicate and
Sure.
see what they say. You can add in vegetation, different wind models, vertical mapping, things like that.
And sometimes you, go on.
One thing I wanted to mention, now that you touched on the wind turbines, someone said earlier about, in politics right now, they put a wind turbine project on hold. So one of our projects, the solar, is with the New York Power Authority, but then we have that Department of Energy project with the battery. So we had to take into consideration, what if they pull the funding for one? So they're both separate projects, so not dependent on each other. So if the battery happens, it doesn't affect the solar. If the solar, if one doesn't happen, it doesn't. So we took that into consideration. They're two separate projects, just same site, because we thought about, what if something loses funding?
Yeah. I kind of wonder, okay, let's call the batteries non-renewable and they're just going to be day-night load leveling. And maybe if you take off the word renewable solar, remove all that, maybe it's okay.
Well, there have already been changes in
Yeah,
what we can and cannot do with that federal grant, but so far it's holding, because I think that's the kind of, particularly since it's American sourced minerals and non-rare earths. I'm semi-confident that grant will not go away. It's already under contract.
yeah. And I think actually that causes a worry when you're thinking about potential opportunities. But the fact is, there's pressure on our energy sources. There will be, and there are people on the left and right that realize we need diverse sources. So I'm confident.
We'll get through this. Yeah, I actually think that this future of heat pumps and energy storage and solar generation and wind and maybe nuclear power has a big future. That's not stoppable. That is going to happen, like it or not. That technology is coming.
So last year, Lachlan and I had the opportunity to go to Denmark. We were invited by the government to look at some of the heat pumps, and we went with a bunch of different partners from New York State, and we went with regulators. So that's a career path too. Energy regulations, helping regulate how things are done in New York State or at the federal level. So that's another career path in energy is regulation.
It's actually super interesting because they're all components.
Right, if you're making the laws, hopefully you know about the topic you're making the laws about, right?
My father was super far to the right. This is what always gives me hope. When I walked into his house 15 years ago, he said, "Look at those compact fluorescents. Do you know how much they saved me?" And he actually took out his bill. So there were financial savings. Didn't matter who was in favor of the technology. I would like to thank you both for coming out and speaking to us.
Thanks for having us.
Super
Thank you.
Interesting. It's amazing work. It's so complicated. I don't know how you do it. I didn't say that a lot. You guys can all do it.
This is just one piece of it, There's a lot of we have a lot of people in facilities planning, so we have some.
We simplify the models enough until we can solve. We don't worry about all the complicated stuff.
So
Physics is really easy.
are there opportunities for students to do interns? We have monies now.
Yeah, absolutely.
Internal internships on our campus. We're trying to grow that. And there sound like amazing opportunities that you just explained that you could get students involved in. So is that something you all do?
Yeah. We've hosted students for internships for project management, health and safety, particularly when some of these projects start coming along, I'd love to be able to set up opportunities with the companies to
Yeah.
internships with those companies.
I'd like to sort of jot down some notes related to that sort of thing, and maybe we can talk again.
Sure.
Because I think it'd be good opportunities. And thanks again. It's exceptionally nice of you to come and join us. Thanks for your work. Just so you all know, so the next one is October 9th, so that's 2 weeks. We sort of do 2 weeks. Barry Clyde is a class of 95, so he's younger than me, but still old.
Sorry.
You're not saying that out loud. No, it's okay, Michael, I understand. I knew what was in your head before you said it.
Well, Andrew's not here, someone has to pay.
I get it, I get it. He owns an engineering company, thanks again. So does a wide variety of engineering. Peter Hoffman, 07, so again, he's getting up there. But he does sustainability for the dormitory authority. So if you lived in the dorms, he's the oversight of sustainability and energy for all of the dormitory authority. And then Robert Merrill is the last speaker for the chemistry people, maybe. He does X-ray characterization of materials. XOS is the company, and they build things that do X-ray characterization of materials. So they're X-ray spectrometers that you might do at some point. So that's who's coming the rest of the semester. Thank you all for being here. Really appreciate it. It's good to have a turnout. Keep telling people, okay? And you know, if you ever had questions, don't take questions. Sure, take them right on cue. I'm gonna take some questions too myself. But, all right, and I've seen the presentation twice now, so I still have questions. All right, thank you all. Have a wonderful evening.
If you haven't already, be sure to scan the QR
You
code.
made it, just in time, Mr. Man. Switch items.
This last.